Hello everyone. I am Priyanka Sharma from the Department of Mathematics, Indian Institute of Technology, Patna. I will be your NPTEL PMRF teaching assistant for the course Introduction to Group Theory, which is NOC26-MA12. This course is offered by Professor R. Venkatesh from IISc Bangalore. So let's wait for a couple of minutes so participants can join this. Okay, so let's start. So this is Introduction to Group Theory. So in the first tutorial, we will learn uh, the notion of groups, its examples, what is order of a group, and order of its elements. Then we'll discuss some abelian and non-abelian groups. Then we will have some problems on particular groups like uh, integer groups, matrix group, symmetric group, and subgroups. So let's start. So first of all, we will understand what is a binary operation. So to define a binary operation, we need a set and its elements so that we can perform some kind of operation. And this operation is performed on two elements at once. So this is known as a binary operation. So what is its definition? So a binary operation, say star, on a set, say S, is a function given as star from S cross S to S. And this is defined by some A and B, and this is mapped onto A star B for all A and B in S. That is, we took the Cartesian product of the set S, that is S cross S, and then we took ordered pairs A and B, and under this binary operation star, this element AB is mapped onto A star B. So with the notion of binary operation, we define the concept of groups. So what is a group? So let G be a non-empty set and star be a binary operation on G. Then the ordered pair G and star is called a group if the following conditions hold. So the first one is associativity. That is, whenever we take three elements in G, say A, B, and C belongs to G, if we preserve the order, then we can perform this binary operation with respect to any pair like A star, B star, C. This will be same as A star, B star, C. That is the order, which is A, B, and then C. This is preserved. Then this won't matter if we compute first B star C and then with A, or A star B with C. Okay, so the second condition is existence of identity. That is, there exists an element, say E belongs to G, such that A star E and E star A, they both are equal to A again. And this satisfies for all A belongs to G. And the third one is existence of inverse of each element of G. That is, for any A belongs to G, there exists an element A inverse belongs to G called the inverse of A in G, such that A star A inverse and A inverse star A they will give us the identity element. And this condition is satisfied for all elements A in G. So if this algebraic structure G comma star satisfies these three conditions, then it will become a group, or we say that G is a group under the binary operation star. Now, what is an abelian group? So, for the same structure, let G star be a group, then it is said to be an abelian group if the binary operation star is commutative. Uh, Hello participants. Can you unmute yourself? Vaibhav, hello.
Hello, hello. Yes, ma'am.
Am I audible?
Yes, ma'am.
Okay, and is the screen visible?
Yes, ma'am.
Okay, so till now, I just summarized the definition of group and what is an abelian group. So I'll prefer if this session will be interactive. Okay, so you can unmute yourself whenever you need to ask some question, or whenever like the audio or video is interrupted. Okay,
Okay, ma'am.
okay, thank you. So an abelian group is sometimes called an commutative group also. So there are some points to keep in mind. I would like to mention some remarks. So the first thing is that we mentioned that the set G is to be a non-empty set. Okay, so actually the second property, existence of identity, this axiom makes sure that the group will be non-empty. Okay, so like whenever we take a set and it is claimed to be a group, identity will be there, so automatically this will be non-empty. Okay. Existence of identity assures that a group is non-empty. And in some books, you can find four axioms. The first one will be closure. Okay, so basically you can see how we define binary operation. This is defined for all elements A and B of a set S, and the operation like A star B. This is again go to the set S. Okay, so from this we can say that the binary operation is closed in itself. Okay, so the first axiom, that is the closure axiom, that is inbuilt actually. Okay, so closure is obvious by the definition of binary operation. Okay, And the identity element is unique in a group. That is, we will have one and exactly one element, which is the identity in the underlying group. Okay. And similarly, inverse of each element of a group is unique. That is, every element of a group will have an inverse, and any element of a group cannot have more than one inverse. Okay. So these two, like third and fourth remarks, these are like pretty obvious. We can prove this using the contradiction method. Okay. So, okay. For G star. So sometimes we represent group by G only. Okay. So whenever the meaning of star, that is the binary operation, that is obvious, we can simply say that let G be a group. Okay. And in place of A star B, we simply write AB. Okay. So if whenever like AB is written, it is understood that we are talking about A star B. Okay. Now, what is a finite group? So a group will be finite if it will have finite number of elements. Okay. And let G be a group. Then G is called finite if it has finitely many elements. Otherwise, G is called an infinite group. And the number of elements in a group G is said to be order of G. And it is denoted by either order of G or sometimes like this. Okay. So now we discuss about some examples. Simple examples are from set theory. That is, we can check that Z plus, this is a group, the set of all integer, this form a group under the binary operation addition. Okay. And can you say like Z with respect to the usual uh, multiplication, that is Z star, is this a group? So no, this will not a group. Okay. So this is a group and this is not. And simply we can check like few, that is the set of all rationals, the set of all real numbers, the set of all complex numbers. These are also groups with respect to the operation addition. And if we want to use the operation multiplication, then we need to remove the zero element, okay, because zero cannot have an inverse. So q minus with respect to multiplication, similarly r minus 0 and c minus 0, these all are multiplicative groups. Okay. Then we have matrix groups. So like M, N, Z. So what does it mean? This is set of all n by n matrices over Z. Okay. That is all n by n matrices whose elements are coming from integer group that will known as M and Z. Okay. So does M and Z form a group under some operation? So yes, M and Z with respect to addition, this is a group. And similarly, if we replace this Z with some field or some commutative ring, so that will again form an additive group. Okay. Now, okay, some interesting groups: general linear, which is denoted by GLN, and here we will have some, okay, say some field F. So what does it mean? Actually, I am recalling the lectures. Okay, so did you watch all the lectures of first week, Vaibhav?
Yes, ma'am.
Okay, so basically I'm giving a summary of lectures so that we can start. Okay, so actually without theory we cannot jump to examples. Okay, so what is GLNF?
Um, Ma'am, I think I have to revise. Like I forgot.
Okay,
Can I
okay,
ask
no
a
problem.
question here? Uh,
Yeah, sure.
in the third example, like uh, you have taken the plus addition operation. Can I
Mhm.
take the multiplication also? Like M and Z, comma multiplication will form a group or not?
Okay, so actually that's why we are going to general linear group. So you want to ask this one, okay?
Yes, ma'am. Yes, ma'am.
Okay. So, no, actually, there will be some problem. Like for this to be a group, you need to check like these three conditions. Okay. So, can you think about inverse? Actually, you need to keep this thing in mind, like this Z dot, that is the set of all integers. Does this form a group under multiplication?
I think no, it will not.
Yeah, so yes, so that's why, like a simple counter example can be this. If you take n is 1, okay, n is 1 means the set of all 1 by 1 matrices over Z. Okay, 1 by 1 matrices means you will have only a single element. Okay, like one row and one column. That is, in this case, for n is equals to 1, m and z dot will become z dot. Okay,
Yes, ma'am.
so, and this z dot, this is not a group, like inverse you can see, that will create a trouble for you. So, like this is the idea why this m and z dot is not a group. Okay,
Okay, ma'am.
like you can simply have any like for counter example, basically you need to fix n. So you can take n is 2, n is 3. So just take any 2 by 2 or 3 by 3 matrix where entries are coming from Z, and check whether like inverse will be again from M and Z or not. So just take any 2 by 2 matrix, find its inverse. Okay, like we all know how to find inverse of a matrix. Okay, so like say I'm taking A, B, C, and D. Okay, so its inverse will be some A dash, B dash, C dash, and D dash. Okay, and if A dash, B dash, C dash, D dash, if any one or like more than one, but exactly one from this A dash, B dash, C dash, and D dash are not coming from Z, like if they are non-integer, then obviously like inverse property fails. Okay.
Yes, ma'am, got it.
Okay. So actually, this is the reason why we need to define general linear group. Okay, so whenever we will have Mn, say R, where R is some commutative ring, we can say that this is a group with respect to addition operation. But what about multiplication? Can we define some groups under multiplication operation, and we are dealing with some matrices? Okay, so general linear group, this gives the answer, that is yes, we can define. And how? So what is this GLNF? So actually this index, whether this is in MNZ or GLNF, so this index represents the size of matrices. Okay, so GLNF means obviously we are dealing with n by n matrices. Okay, and this F, like the whether this is a ring or a field which is written in parenthesis, this is uh, this is the set basically where the elements of matrices are coming from. Okay, so what is GLNF? GLNF is not simply the set of all n by n matrices coming from the field F. This is the set of all those m by n matrices whose elements are coming from the field F, which are invertible. Okay, because we see in MNZ dot, basically inverse property fails. Okay, so we need to make sure that we will have inverse of all elements. So for that we can simply consider the set of all those matrices, or like we can start from all those matrices who are already invertible. Okay, so that we will have the inverse of all elements naturally. Okay, so this is GLNF is basically set of all, say either non-singular or invertible, n by n matrices over a field F. Okay, or symbolically we can say that GLNF is basically the set of all matrices, say A, which is Aij, these are n by n, that is I and j are basically 1 to n, such that determinant of A is non-zero. Okay, so this is general linear group. Okay, general linear group is basically a subset of the set of all matrices in which we already preserve the um, existence of inverse. Okay, now we have one more thing, special linear group, which is SLNF. So this is basically a subset of this GLNF. And what is special in this? Only the thing is that the determinant, this determinant is 1. Okay, that is, sorry, SLNF is A such that determinant of A is 1. Okay. So general linear group and special linear group, these are defined over some fields. So we can have like, see this, GL2R. So this means uh, all non-singular 2 by 2 matrices uh, whose elements, like if we are taking A, B, C, and D, then all these A, B, C, and D are coming from the real numbers. Okay. We can have SL3, say we define over complex field. Okay. So any doubt till now? Okay.
No,
So,
ma'am.
okay. And similarly, we can define this Rn plus. What does it mean? So Rn, or like simply if we took R square or R cube, okay, like Euclidean plane in that. So here we have elements in the form of tuple. Okay. In R3, we will have three tuples A, B, and C. Okay. So Rn plus, this will be the set of, say, A1, A2, An, that is n tuples where Ai's are coming from R. Okay. So this forms a group under addition. And how we define this binary operation addition? We define it point wise or component wise. Okay. That is, whenever we take, say, some A is A1, A2 up to AN, and B, which is B1, B2, Bn. So A plus B will be defined as A1 plus B1 up to An plus Bn. Okay. So fine. So mm, okay. One more thing. What is a subgroup? So as we have subsets for a set, so similarly we can have a subgroup for a group. So to define a group, basically we had a binary operation. Okay. So if G star is a group, then this star is defined from G cross G to G. But we are willing to define its subgroup. So first we need a subset. So let H be a subset of G, and obviously it should be non-empty as we are defining some group type of notion. Okay. So say this is not phi. And again, we are claiming that this H will be a subgroup. So we need some binary operation. So we use this star only for uh, H. And how? We restrict it to H only. That is star, which is restricted to H cross H. And this is defined from H cross H to H. So these ordered pair H and star restricted to H cross H is a subgroup of G if first one, this operation is closed, and second one, this structure is a group in itself. Okay. Symbolically, we define it as this, uh, this one means H is a subgroup of G. Okay. So, for example, we discussed that R plus is a group, and we know that Z is a subset of R, and this is non-empty. And this Z again forms a group under the same operation. So this Z is a subgroup of R. Okay. So now come to some questions. Determine which of the followings uh, these are associative. Okay. So the first one is the operation star defined on R, that is real numbers, by A star B is A plus B plus AB. Second, the operation star defined on Q by A star B is A plus B by 5. Third one, the operation star defined on Z cross Z by AB star CD. This is AD plus BC, comma BD. And fourth one is the operation star defined on Q minus 0 by A star B is A by B. Okay. So when we say that an binary operation is associative, whenever like A star B star C is same as A star B star C. Okay. That is, we can reform the brackets. Okay. So is the first operation, is this associative? So when like how we check it? Let A, B and C belongs to R. We need three elements. Okay. And A star B star C. So this will be A plus B plus AB, and then star C. So this will be, how we define A star B? A star B means, see here, A star B is sum of those two plus product of those. Okay. So here, what will be A plus B plus AB star C? This will be A plus B plus AB plus C, that is sum, and then product of those two, that is A plus B plus AB C. So this will be A plus B plus C plus AB plus BC plus CA plus ABC. Okay. Similarly, we can compute this A star, B star, C. So can you check what will be this? This will be same as uh, this one. So simply check. Are they same? I'm giving you 1 to 2 minutes. Can you check it? What will be B star C? B star C will be B plus C plus B C. What will be A star, this new element? This will be A plus B plus C plus B C plus their product. So this will give us the same one. A plus B plus C plus AB plus BC plus CA plus ABC. So yes, these two are same. So we can say that the operation is associative. Okay. What about the second one? The second operation, that is star defined on Q by A star B is A plus B by 5. So is it associative? So you can simply have a counter example. So it's up to you. You can take A, B, and C in abstract form, or you can take particular choice like say 2, 3, and 5 instead of A, B, and C. Okay. So I'm taking A, B, and C belongs to Q. What will be A star B star C? This will be A plus B by 5 star C, means sum of these two by 5. That is A plus B by 5 plus C by 5. So this will be A plus B plus 5C by 25. And what about A star B star C? So this is A star B plus C by 5. Okay. So this will give us, okay, A plus B plus C by 5 just divided by 5. So this will be 5A plus B plus C by 25. So yeah, obviously they are not same. Okay. It means the operation star on Q defined by this example 2, this is not associative. Okay. What is the third one? Z star Z. So is this associative? How we define A star B is, okay. Okay. Actually, we are taking Z cross Z, that is the Cartesian product of Z by itself. So elements will be in ordered form. Okay. So this will be A B star C D. This is A D plus B C and B D. Okay. Means the first tuple will be product of the first and last A and D plus product of these two B and C. Okay. And the second one will be the last tuple of both the elements. Okay. So what will be the associativity here? Okay. So for this we need three elements. Okay. A, B, C, D, and say E, F in Z cross Z. Note that this E here is any element in Z. This is not exactly the identity element. Okay. So don't get confused with this. What will be AB star B C star CD? This will be A comma B star. So what will be this? This will be BD plus, sorry, CD and EF. Okay. So this will be CF plus DE and DF. Okay. So this will be, now again we will have first and last, and these two. Okay. So this will be ADF plus B into CF plus DE, comma, this and this. That is BDF. Okay. So what do you think? Whether this operation star will be associative or not? Okay. So we simply have this. Now we can compute AB star CD, and then we operate this with EF, and we compute what will be this, and check whether these two expressions are equal or not. So can you check it? So is it easy, or like you will get some difficulty, or there will be some confusion? Anyone from you?
No, it's
Okay,
easy,
so
ma'am.
can you check it? Like this will be an easy one. Can I leave it, or
Yes, yes,
like,
yes,
okay?
yes.
So yeah, actually, this operation is associative here. These two expressions will be same. What is the fourth one? Okay, so A star B is A by B. That is, we are taking the division as the binary operation. So what is the guess? Whether this will be associative or not?
No,
Like,
no.
no, yes, like A star B, and then we operate it with C. Whether this will be same as A star B star C. No, this will not. You can simply have a counter example, like take anyone, like 2, 5, say 25, and check whether these two are same or not, or whether in general you can do it. Okay, so no, this is not. So can you complete it?
Yes.
Okay,
Yes, ma'am.
okay. Now come to second question. Determine which of the following sets are groups under given binary operations. So the first one is the set of rational numbers with denominators equal to 1 or 2 under addition. Okay, so first we discuss this one and then we come to the second one. Okay, so we are not taking the entire set of rational numbers. Like we are not taking all p by q where q is like non-zero. No, we are taking exactly those p by q such that the q is either 1 or 2. Okay, so say the set is p by q belongs to q such that q is either 1 or 2. Okay, so the question is S plus a group? So for this, we need to take two elements and check whether this operation is closed or not. So let A and B belongs to S. Then what will be the form of A and B? So there can be some cases. So case one is A is of the form P1 by 1 and B is of the form P2 by 1. Okay, that is both have 1 as the denominator. Okay, then what will be A plus B? This will be simply P1 plus P2 by 1. So which is again in the set S. Okay, as we have the denominator 1. Case 2. When A is P1 by 1 and B is P2 by 2. Okay, then what will be A plus B? This will be 2P1 plus P2 by 2. So now, what about this A plus B? It has 2 as the denominator. So this will be an element of the set S. Okay, this 2P1 plus P2, this is an integer and 2 is the denominator. So simply we can say that this is an S. Okay, case 3, if A is like P1 by 2 and B is like P2 by 1, then again A plus B, this will be P1 plus 2P2 by 2. So this will be in S. And the fourth case, when both A and B have 2 as the denominator. Okay, so A is P1 by 2 and B is P2 by 2. Then A plus B will be P1 plus P2 by 2. That is 2 is the denominator. So this will be again in S. Okay, so actually we cannot have any other case. Okay, whenever we take two elements in S, either of this case 1, 2, 3 and 4 will arise. Okay, so yes, the operation addition is closed in this situation. Okay, so closure property holds basically. Now, what about the associativity?
It holds.
So it will hold. Why? Because addition is associative, okay, over the entire queue. So this will be like addition will be associative for any subgroup of or any subset basically, any subset of Q. Okay. So if associativity holds in a set, it will be automatically hold in subset of that. Okay. So associativity is obvious here. What about identity?
Yes. Identity 0.
Because we can write 0 as 0 by 1. 1 is the denominator, so that will be in S. E will be 0, that is 0 by 1. And what about inverse?
Yes.
Yes, so for any A belongs to S, either A will be P by 1 or A will be P by 2 for some P belongs to Z actually. Okay, so inverse of A, that is minus A, that will be minus P by 1 or minus P by 2. Both are in S. Okay, so we will have inverse of every element. So yes, these structure S plus form a group. Now, I have a question. Here we take all those elements from Q which has either 1 or 2 as the denominator. Okay, actually 1 is the trivial one, which is needed for the identity, you can see. And other than 1, I allowed just one number. Like I can replace this 2 by any other integer, other than 0 actually. So
Excuse me,
what?
ma'am.
Yes.
Hello, ma'am. No, today I have one more class. There is a clash between my courses. No, this live interaction classes. I've
Okay.
taken one more course geometric algebra with commutative algebra, something like this. One more course is there.
From NPTEL
So
itself.
yeah. So
Okay.
timing it is clashing, ma'am.
Uh,
I've taken 3 4 courses, so all the
mhm.
dates are given today only,
Okay.
and timings are clashing. Your timing is 6 to 8, and their
Mm-hmm.
timing is 7 to 9.
7 to 9. Okay.
Yeah, so what topics you are going to ma'am? Basics, though I know here a little bit, but
Okay. Okay.
I am facing the problems in subgroups, no, order divide subgroup,
Okay.
something like this, cosine, how it forms a normal subgroup, and then when we go in the depth, no, there I
Yes, I
started.
understand. See, actually, all the sessions, whether this will be mine or your like
Okay,
next tutorial session,
it will be there
yes,
on there.
and
So
this will be
today,
uploaded on YouTube channels.
okay, ma'am, today, what topics you are going to just discuss, so that I can, if it is
Uh,
not urgent,
okay,
can you?
okay.
Okay,
I'll discuss some more examples of groups, subgroups, and some subgroups of symmetric groups. That is like, and especially I'll focus on permutations and operations on them, like what will be the inverse of a permutation and how we define some power of a permutation and what will be the multiplication of them, what will be the cycle decomposition of a permutation, and
okay,
some subgroups of general linear and special linear
okay.
groups.
This alternating group also comes under the permutation group only. Alternating group.
Mhm.
Okay. So actually, I lack that concept. Actually, I want to attend this part also. So there
Okay.
also.
Uh, Actually, like I understand. Like as a student, I also got confused with permutation groups, and especially when we need to perform
Alternating.
some operations on them. So yeah, that's a bit confusing. So yeah, after that we will discuss
Okay. So
like some
just now after
permutations
10.
in a symmetric group.
Okay. So just now, after 10 15 minutes, I'm just coming back, because I'll see that what topics they are going through. Uh, I'm just returning back
Okay,
within
sure.
5 minutes.
Uh, Okay, like one more thing which you can do, like you can join both meetings from different devices, like one from your phone and like another from laptop or anything else. And then
Yeah.
you can simply see which topic is being discussed and you can join
Yeah.
as per your preference.
Okay. Thank you.
Okay, okay, sure. Thank you. Okay, so my question was, what about this? S plus, where S is P by Q belongs to Q, such that P belongs to Z and Q can be either, sorry, 1, 2 or 3. Okay, so in the first one, we have just two choices of denominators. So here we have three choices. So will this be a group again or no?
No, no.
No.
No,
Yes.
ma'am, I think no.
No. Why?
Because if we'll take like P1 by 2 and P2 by 3, so maybe it belongs to
Six.
some P1
Yes.
plus denominator will be 6 then overall.
Yes. Yes. So this is not in S. So S plus is not a group. Okay. The third one, if G is this A plus B root 2 belongs to R, that is, now we are taking a subset of real numbers such that A and B belongs to Q. So my question is G plus a group? And secondly, is G minus 0 dot a group? So obviously, like whenever we discuss about multiplication, we need to remove 0 from the set, okay? Because 0 cannot have an inverse. So yes. So what about these two?
First
Which
one,
one?
first one will form a group,
Okay.
and second one, it's multiplicative inverse will be also there, and identity will definitely will be there, and because 0 is not included in this,
Mm-hmm.
and
Exactly.
multiplication associative also will be there, and closer to
Mm-hmm.
definitely will be there. So second also will form a group.
Okay. So like yeah, associative will be there in both cases, because whether this is R plus or this is R minus 0 dot, both are groups, okay? Both these structures satisfy associativity. So we will have associativity of this operation plus and dot for any subset of R with respect to plus, and R minus 0 with respect to dot. Okay, so associativity is trivial. Then we need to check the closer one. Okay. And the most important thing is that we need to figure out what will be the identity in each case. Okay. So, other participants, can we do it? Like the first one, G plus.
Ident
So,
identity will be 0.
yes. Uh, what will be for G plus? Is it closed? So, yes, we can take, say, X is A1 plus B1 root 2 and Y as A2 plus B2 root 2. And then X plus Y will be basically A1 plus A2 plus B1 plus B2 root 2, where these two, A1 plus A2 and B1 plus B2, this will be in Q. Why? Because Q is itself a group with respect to plus. Okay. So A1 and A2 both are in Q. So A1 plus A2 will be in Q again. Okay. So we can say X plus Y is in G. So this is closed. And the identity, that will be 0, because 0 can be written as 0 plus 0 root 2, where both, like 0 is a rational number. Okay. So yes, the additive identity will be in the group G. So identity is there. What about inverse? So for any a
Yes.
plus b root 2, we will have x inverse as minus a plus minus b root 2. Okay, so we can verify that this will be inverse of x. Okay, and x was arbitrary, so we will have inverse of every element. Similarly, we can verify whether this is a group or not. So can you do it? Or we need to discuss this?
We can do.
Hmm. We can do it.
Okay. So we just try. If you will find any difficulty, then we will discuss in the next session. Or we can do one more thing. I'll share this PDF with you all. So I will give the detailed proof of the second part also in that PDF. Okay. That will work, I guess. Okay. Next one. If G is defined as Z belongs to C such that, actually I'm comfortable in writing this way. Zn is 1 for some n belongs to Z plus. Okay, like all those complex numbers for which like whose nth power is 1 for some natural number n. So basically this G is the set of all roots of unity. Okay, so the question is whether G plus a group. So is it a group with respect to plus? Okay, not with respect to multiplication. So first check whether this operation is closed. A simple counter
It
example
is.
we can take.
Yeah.
Mhm.
Uh, uh, this will be since it is a cube root of unity, so I think it will be there.
Uh,
Like
okay.
I, I,
First of all,
say,
yes.
because cube root, I think nth root of unity, every element
For
must have.
every n. Okay, so like G will be the set of
Okay, it is positive, no? Z positive. So I think you're defining on and n belongs to Z positive. Okay. So multiplicative.
like
I think inverse also will be there. Identity will be definitely will be there.
identity with respect to plus.
No, not with respect to plus. Like
Yeah, that's
with
why
respect.
I'm emphasizing
Yeah,
on this that the
no,
addition is
yeah,
the
yeah, yeah.
binary operation, not the multiplication one. This is the twist, okay? With respect to multiplication, you can say this will be the like this will be a group, okay? Two things we need to keep in our mind. First one, we have plus as the operation, and the second thing is that we are not taking only square roots of unity or cube roots of unity. We are taking all nth roots of
And
unity, like for all
and
natural numbers n. Okay, so with respect to plus, this will not form a group. Obviously, identity will not be there, and like initially the closer holds, like one will be in G. Okay. Mm, for n is equals to 1 actually, but 1 plus 1 is not in G. Okay, as like 1 plus 1 is basically 2, and we cannot find there is no n belongs to Z plus or say n, like there is no natural number n such that 2 to the power n is 1. Okay, this is not possible actually. We are taking Z plus. 0 is not allowed. Okay, 2 to the power 0 will be 1, but we are taking only natural numbers. 0 is excluded from there. Okay, so yeah,
uh, uh,
initially closer
if
fails.
if if zero is allowed, then like if we'll take zero, z only if you take z,
Okay,
then
you are willing to modify the definition.
no,
N
no,
belongs to.
n belongs to z. If you'll take, then also it is not possible because n can be any value, or it will surely for n equal to zero, it will come.
Okay, so which case you are discussing about? N belongs to
This one,
this or N belongs to this?
n belongs to okay, there are two further cases now divided. Both are different, no? I'm
Yeah,
take
both are
talking
different.
about n belongs to z. First of all, we talk this.
Okay, this one, like the. Mm, okay. So, can you have identity? What is the additive identity? Okay,
Identity is
that
zero.
is
Zero.
0. Hmm.
Yeah.
And yeah, so 0 can be written as 0 to the power something. Can that be 1?
Okay. No. Zero
Mm,
power anything will not be one.
yes. And I think uh, we cannot have. Okay, what about closer? Will this operation be closed or not? Say A and B belongs to G, then A to the power n is 1 and B to the power m is 1 for some n and m belongs to say Z. So we need to discuss about A plus B to the power we need say some k. This should be 1. Does such k exists? So actually 0 works here. Like if we take either this or this, 0 will be included and this will be a sub case, no? Like say G dash will be Z belongs to C and we know that Z to the power 0 is 1. So this will be a trivial thing actually. Okay.
Yeah, got it, ma'am. Like simple,
But
if you
what about
if we go with the like a counter example, like if I take just the cube root of unity, if I'm taking suppose for instance, or if I'll take the fourth root of unity. So
Mhm.
yeah, fourth root of unity, if I'll take, so one minus one iota and minus iota are there. So
Hmm.
under plus, if I'm considering, so it zero it is coming, and zero doesn't belongs to that particular group.
Yes.
So under addition, so it is not forming a group. If we'll take a
Yeah,
counter
exactly.
example, like so
Yes.
mathematically, it's I think will face problem because language is somewhere no very typical. uh,
Yes, actually, yeah, that is the case. Like we are taking all those complex numbers whose like power 0 will give us 1. So
Yeah.
for any non-zero number, this is true.
Okay, ma'am,
But
can you help in that one more? Like same example, I found it very interesting, but I was not able
mhm,
to understand that part. Actually, that's why I've taken the this group theory course because wherever
okay,
when I'm going to study anything, everywhere it is coming very vast, na? Whether it
okay,
is a or whether it is a competitive algebra or whatever it is. And
exactly.
Galva, I've joined the Galva theory also, but actually
Mhm,
not a single line was I was able to understand because of the basics. I was lagging. Although I have done my like graduation, MSc, everything I've done, but you know that just the for the sake of like now what the theorem we have got, we have learned, we have written, but we are not understanding actually what is happening. Now,
mhm,
since I'm interested to understand the depth of this, so I'm finding
okay,
it's very useful because what I realized ki it is again the LKG class for me. Like how we do the addition, subtraction, multiplication in the junior classes. Actually,
Okay.
that thing was in the mind, but actually addition, subtraction, division is, I think, this is again redefined. What I think so. So
Yes.
here problem I that was for the the 17th root of unity in the complex number,
Mm-hmm.
uh, and that it was shown ki, like it forms a group. So
Mm-hmm.
there they
With
have
respect
taken
to
the roots
multiplication.
with respect to multiplication. So what they
Mm-hmm.
did, whatever the roots are, 17 roots of the unity are there. So
Mm-hmm.
definitely, suppose if I take zeta 1, zeta 2 up to zeta 16. So
Mm-hmm.
they have very beautifully they have divided this group into the two groups. I don't know how they have done. Like first zeta 1 is compatible with zeta 1 plus zeta 16 plus something, and second group with the zeta 3
Okay.
and so on. So and ultimately they have actually it was a problem of polynomial factorization, like
Mm-hmm.
uh, uh, zeta power 7 x power 17 minus 1 equal to how he has factorized ki one group with the x minus zeta 1, zeta 14, and so on. He has taken with the means he has divided with this all 16 groups into 8 and 8 groups. And further, he has
Okay.
divided into 8 groups. And ultimately, he has got this equation like t square plus t minus 4 equal to 0. And then he has solved key 1 plus under root of 17 by 2 equal to 0. I think maybe you're also familiar with this. Actually, this was
Mm-hmm.
the problem of the Gauss one, no? Like 17 side polygon will be made no in the circle, unit circle.
Yes.
This concept has been uh, uh, used there. So can
Mm-hmm.
we have that one like 17 group, we can see that what is happening in that.
Mm, see, like, the thing is,
Okay, we can
your question
further.
requires, see, like,
Okay, more
yeah, no
depth.
problem. That will require
I
some
think
more basic notions,
yeah, yeah.
which could not
Okay,
be familiar with other
later on.
candidates.
Okay,
One thing I can do, do you have the link of my YouTube channel actually?
your YouTube channel link I didn't have, ma'am. Uh,
Uh, that will be shared with you all. Okay, fine, no problem. In this PPT itself, this PPT will be shared with you all. And here I mentioned my YouTube handle. So one thing I can do for you, I can make a video on this topic and I can upload it on that channel.
thank you, ma'am. Thank you, ma'am. Thank you.
Okay. And one more thing, there can be some topics which will not be able to cover in today's class. We can discuss in next class, and you can have doubts in this one, or there can be some other doubts. So you can ask in the comment section of that YouTube channel and comment section of this video. Okay. So I'll try to resolve those queries. Okay. Whether in the comment box itself or if I'll find that I need to make a separate video, a short video of 2 minutes, 5 minutes accordingly, I'll make that. Okay. So I'll be happy if you all will interact with me. You all will be like active. Okay. So just make sure your participation is active so we can uh, we can get more benefits from this course. Okay. So next one. Let G be a group such that AB inverse is A inverse B inverse for all A and B belongs to G, then which of the followings These are true. First, G is finite. Second, G is infinite. Third, G is abelian. Fourth, G is non-abelian. So actually, my first question is how we define. Wait. This is actually A, B whole inverse. Okay. How we define this in a group. So
Yeah.
A, B inverse is B inverse, A inverse. Okay. For all A and B belongs to G. Why? Actually, it means inverse of AB is B inverse, A inverse. Okay. So we can check what will be this AB and AB inverse. Like we know that this is the identity. Okay. And we are saying that the value of this, that is the inverse of AB, this is B inverse, A inverse. So this will be true if AB and to B inverse, A inverse, this will be the identity. So what will be this? This will be A, B, B inverse, A inverse, as operation multiplication is associative. This will be A identity A inverse, because B and B inverse are multiplicative inverse of each other. Now this will be A, A inverse, and this will be the identity. Okay. Yeah. We are just discussing these topics as like some problem solving session. This is actually. So I'm doing this in mm, a short way. I'm skipping this results here. So whenever you will write the proof in your graduation or post graduation course, you need to write this. Okay. So you will write here like the operation is associative and this as like B and B inverse are inverses of each other and all that. Okay, I'm leaving that. And similarly, we can see that B inverse, A inverse, AB, this is identity. So that's why we say that inverse of AB is defined as B inverse, A inverse. Okay, so this is the actual form. Okay, but in this question, like this is already we have AB inverse is B inverse, A inverse. And in the question, what we have given is that AB inverse is A inverse, B inverse. Okay, then what we can say about the group?
Abelian.
So yes, this will be abelian. Why? What we need to
AB inverse is same as BA inverse.
yes, or what we can claim for a group to be abelian, like AB will be BA, right? Now, say we consider what is AB. So AB can be written as AB inverse, and again we will take its inverse. So this will give us AB again. Okay. So what is AB inverse? Uh, See, we need to take inverse two times. So one time we can use the original definition, and second time we can use the condition which is given in the question itself. Okay. So say first we are applying the condition which is given, that is A inverse, B inverse, and then inverse. And then we are using the original definition, like the original result actually, that will be B inverse, inverse, A inverse, inverse. So this will give us BA. So yeah, the group is abelian. That's a group G. Yes, G is abelian. So this is true. This will be automatically a false statement. What about the order of a group? Whether this will be finite or infinite? It can be both actually. We can have like both kind of examples. A group for which this condition is there and the group is finite, and again the group is infinite.
Like excuse me, ma'am. Like
Hmm.
I have lot of problems in this also. Like whether the group is finite or like when we go modulo n or modulo prime, so
Integer
definitely
modulo,
they,
yes.
so they like quotient group I'm talking about or some, so that is finite. It will be not
Hmm.
I think infinite, but like
Yes.
when we talk about the integers, rationals, okay, so whether the integer set will be finite group or infinite group, and
This one,
rational,
Z.
yeah, z,
This will be infinite.
okay. But ma'am, like in like somewhere they take it as like countable. Okay, it is infinite countable.
Yes.
Okay, like I was
Countably
little
infinite
confused with
actually.
the, like I was thinking like infinite means which we can't count. So that's
Okay, no, 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 no. Infinite doesn't mean that we can't count. Actually, what we need for
to assign
counting
the
we
next
need, like say we have
which
some objects, then we
maximum.
will assign some natural numbers to those
Yeah,
objects.
yeah,
Like this is
yeah.
the first one, second one, third one. So we will have a like one-to-one correspondence between those objects, and 1, 2, 3, 4 up to so on. That is the set of natural numbers. Okay, because we use the set of natural numbers for counting. So whenever we like you can say like whenever we can rearrange the set, or we can correspond the elements of a given set of some objects with elements of natural numbers, that is 1, 2, 3, 4, 5 up to so on, then we can say that the set is countable. Otherwise, this is uncountable. Okay, so if we have a finite, say we have only five elements, say A, B, C, and D, A, B, C, D, and E. Okay, so 1 can be assigned to A, 2 can be assigned to B, C is 3, D is 4, and E is 5. So those A to E, we have 1 to 5. Okay, so we can count those, or we can have a subset of natural numbers which can represent the given set A, B, C, D, E. Okay, so in that sense, that is countable. So again, whenever you will take like the set of all natural numbers, so that is infinite in itself. But if we go counting without stopping, like 1, 2, 3, 4, so yeah, obviously we can, counting will never stop. Okay, so
Okay,
yeah,
but
that is infinite, but
uh,
we can. Mhm.
I have the doubt in this also. If I'll take a 0 to 1, like of the real number, 0 to 1,
Interval.
0 to 1, uh, close interval. Yeah.
Okay.
So is it finite set or infinite set?
Mm, you are taking 0 to 1 as a closed interval. So if you are taking like A belongs to R
R.
such that A is less than or equal, like this is between
Yeah,
0 and
yeah,
1. So yeah,
yeah.
if A belongs to R, then this is infinite, and this is uncountably infinite actually. Okay, and if you say like A belongs to Q such that this A is between 0 and 1.
So
Okay,
it will
then
be countable,
this will be finite,
finite. Okay. And countable also.
countable also. Every finite set is countable. In infinite, we have two categories, either countable or uncountable. Okay,
Okay. I've got little bit idea of this. Thank you, ma'am. Thank you.
okay, okay, okay. So is the question clear? When we take Zn, that is integer modulo n, say Z2, that is 0 in 1. So this is finite and this condition is there. Or we can take the set of all integers, this condition will be there. So mm, G can be either finite or infinite. So both the statements are not true in general. Okay. Partially they are true. Like we can have some examples for which first condition is satisfied. Similarly, for some examples, second is true, but not in general, not for all cases. Like neither one is true nor two is true. Okay. Next one. Consider. Okay, so do you know this result? Let G be a group, then order of an element and order of the inverse of that element are same. Okay, so this is the result actually. Uh, Now what is order? What is this?
Uh, Order of element means a power n will give the identity element.
Mhm. And A belongs to G. So we have a group and we take an element in this. Then the smallest positive integer, say n, is said to be order of A if A to the power n is identity. Okay. That is, if we operate A to itself n times and we get the identity element, then we say that the number n is the order of n. Two things. N must be a positive integer. It cannot be zero. And obviously, we are not handling with negative integers like negative powers of A.
Oh,
And secondly, such n must be smallest.
okay. Ma'am,
Okay.
one more here. I have suppose if I'll take like order of G is M.
Mm-hmm.
Okay. Now I have got a power n is equal to e. N obviously n will be less than
Order of G is n.
m,
Okay.
and order of a is n element.
Okay.
Now it may happen that m and n can be equal.
Yes.
Okay. And n must divide m. It is
Yes.
also compulsory or it is not compulsory.
It is actually, we will study what cyclic groups are. So whenever
Okay,
we'll
okay,
study and discuss cyclic groups, we will come to this again.
okay. Like here in this case, like with that only I have a doubt. Like when we take a power n, so is it
Mhm.
going to means if it is not divisible, then n will be not possible, no? In general.
Yes.
Okay. Means it must be n must be factor of m,
In this case, yes. Divisor actually.
divisor.
Hmm. But obviously, we are discussing about finite groups. Okay. And actually, in the case of order of an element, if no such positive integer exists, like if we don't have some finite n, then we say that order of A is infinite, like A is of infinite order. Okay. So if G is a finite group, we will always have a finite order for all elements of G. But if G is infinite, we can't say. Okay.
Like, can I take 2 minutes more?
Okay.
Its application I've seen in the like junior classes also, because now I am realizing ki it is there in the some sort of things has been already introduced in the like ninth class or eighth class or in the junior classes. Like
Mm-hmm.
when we go the for the decimal representation of 1/7, as 7 is the prime number,
Mm-hmm.
and then they asked whether it is non-terminating, non-repeating, or how many repeating cycles it has.
Mm-hmm.
So like, and for the number 7, as it is prime,
Uh, okay,
so it has
and
6 cycles.
you are
It has,
taking it in some integer modular group now.
yeah. So
Okay.
when we divide by 7, its cycle repeating cycle is 6.
Mm-hmm.
So repeating cycle is 6. So it why it comes, because when we take the modulo 7, we get one I think 1 to 6 we get the numbers, and the smallest power by which 10 power n will generate all the groups, something like it is there in that also. I think it is used in this part. I think it is used over there to get this cyclic, that how many decimal
Yes,
places
but
it is.
actually the problem is integer modular group and cyclic groups. These
We'll do later.
two things are not introduced yet, so
Oh,
we'll
okay,
discuss
okay,
it whether in just next session or next to next.
okay.
Okay. So, uh, okay, and this is denoted by order of A is n. Uh, Alternatively, we can write this. Okay. So the claim is order of A and order of A inverse. They are same. So how can we do it? Uh, Quickly, I need to give you a hint for this. So say order of A is M and order of A inverse is N, permitting the case uh, that M and N are different. Okay, so order of A is M. This implies A to the power M is identity. Okay, and order of A inverse is N. This means A inverse to the power N. This is identity. Now, what about A inverse to the power M? This is basically AM inverse, that is E inverse, that is identity. Okay, that is whenever we take A inverse to the power M, we get identity. Okay, so order of A inverse, this will be less than or equal to M. Okay, actually it will be a divisor of M, you can say. Uh, like we can say N is less than or equals to M from here. Okay, if we switch this, if we take this AM, so this will be okay, say AN. So what will be AN? This will be A uh,
Uh,
AN
ma- uh,
inverse and
ex-
then yes.
Can we go like this also? I think like this also we can do.
Mm-hmm.
A power m is e. Now we will take we'll multiply by the inverse on the both the sides. A power m inverse on the both the sides. So we'll get a power m into a power m inverse is equal to e into a power m inverse.
Mm-hmm.
So on the left side m I'll take common. So it will be a into a inverse power m. So that is
Mm-hmm.
obviously will be e, and the right side identity into any element will be a m power inverse, and then I can switch over the powers. So a inverse power m will be e. So it means ki, its order is same. We can go in this way.
Yes. Yeah,
If
sure, no problem.
yeah,
See, any statement can have alternative proofs, so no
yeah, yeah.
problem. You can use either of them. Okay. So the question is, I don't have much time, and I was thinking to discuss the cycles of permutations also. Okay, no problem. Uh, let G be a group, and order of some A belongs to G is 5 if A inverse is B square for some E is not equals to B belongs to G, then find the order of B. How to do it? See, um, what we have, A to the power 5 is identity because order of A is 5, and B square is A inverse. What will be B to the power 4? That will be A inverse, A inverse. You can associate the operation. This will be A inverse B, A inverse. So this will be B identity B A inverse, which is basically B square A inverse. Okay. Similarly, what will be B8? That will be B square A inverse, B square A inverse. And that is like, I'm not writing all the steps, I'm just giving you a hint. This A inverse A, what will this do? This will make identity. Wait. Okay, this will work, no problem. So this will be B to the power 4 A inverse. Okay. Mm, okay. And actually, here also we can do it. Fine, no problem. Uh, we can put a value of B square here. That will be A inverse, A inverse. So this will be A square, B, A inverse square. Okay. And this will be A square, B, A inverse square, A inverse. So this will be A cube, B, A inverse cube. Now what will be B16? You can see this will be A4, be A inverse 4. Okay, like for 2, we have A to the power 1, B inverse to the power 1. For B4, we have A square, B A inverse square. When we double the power of B, we have A cube, B A inverse cube. When we again double the power, we have A to the power 4, B A inverse to the power 4. So what if we again doubled it? That is B to the power 32. This will be A to the power 5, B A inverse to the power 5. But order of A is given as 5. And if order of A is 5, order of A inverse, that will also 5. Okay. So these two will be identity. Okay. So B to the power 32, this will be E, B, and E again. That is B. Now, G is a group. B is its element. So we will have inverse of B in G. So multiply by inverse of B from right. We will have B to the power 32. Sorry, B to the power 31 is identity. Okay. It means order of B cannot exceed 31. It will be like some divisor of 31. Okay. What are the divisors of 31? 31 is a prime number, right? So order of B can be either 31 or 1. But if order of B is 1, that is B is identity. But we took this, B is not equals to identity, right? Thus, order of B is 31. Okay. Now come to next question. Hmm. Which of the followings are true? First one is, if order of A and order of B is finite, order of AB is also finite. Second, if order of A, order of B are infinite, order of AB is also infinite. So obviously we are taking these elements A and B in some group G. Okay, so we have these two statements. And let's add one more. Order of AB is equals to order of BA. See, AB is not equals to BA in general. If the group is non-abelian, then AB is not equals to BA. So if a group is abelian, then obviously AB and BA both are same. So they have same order. But what in case of a non-abelian group? Like exactly. Elements are different, but can their orders be different or they will be same? This is my question. Okay. So come to the first. Order of A and order of B, both are finite. So can we have like such? Yes.
Is it true?
Mm, think about it. Actually, that is my question only. Is it true? See, I am not specified the structure of group. I didn't say like what the group G exactly. It can be any group.
Okay.
And
So,
for these kind of
since
questions, uh, you need to think like out of the box, just in some bigger case, like other than numbers, you can have permutation groups, you can have, but see, mm, one thing, order of A and order of B, they are finite. And we are discussing whether order of AB is finite or infinite. So we need to take first such a group which is infinite itself. If group G is finite, then obviously AB will be element of G by closure property. So if order of G is finite, order of AB will be finite, obviously. Okay. So to verify, either to prove it or to find any counter example, first you need to pick an infinite group. Okay. So infinite group means symmetric group. No, S infinity. That should not be an easy stuff. We should not do this. We can have matrix groups. Okay. So can we do it in case of matrices?
So matrix groups are infinite, or is it
Mm,
finite?
See, if you are taking this M2R, it means the set of
Infinite.
all 2 by 2 matrices A, B, C, and D. I'm not specifying that this is the spatial linear or general linear. No, just matrices such that A, B, C, and D are coming from R. So if we have just one element A and that is coming from R, that is we have choices from the entire R. Okay. So that means we have already infinite choices for A. Okay. And here we are taking A, B, C, and D. So 4 times we need to pick some number from the set of real numbers. Okay. So we can have infinitely many such matrices. So this will be an infinite group. If you take R, the field or the ring in case of additive groups, if this underlying structure, whether this is R, whether this is Q or C, like if this is infinite, the matrix group will be infinite. If this is finite, like if you take M2 over Z5, this will be finite. Okay. Because in that case, A, B, C, and D will come from Z5. Okay. Excuse me. Okay. So I'm not taking any finite fields. Otherwise, the matrix the matrix group will be finite, and we need an infinite group to find counter examples. By saying counter example, I'm already given you a hint that this one is not true. Okay. So I take some matrices A and B whose orders are finite. So let's say this 0, -1, 1 and 0. This is the metric, and 0, 1, -1 and -1. So you will find A square and check whether that is I2, that is 1001. If not, you will check A3. If not, you will check A4. So I'm saying order of A is 4 and here order of B is 3. Okay, both are finite. Can you do for uh, the matrix B?
Yes, we can do this.
B is 0, 1, -1, and -1. So what will be B square? This is simple actually, simple matrix multiplication. Check what is B square and what is B cube. Which one is I2?
Not there. I2. BQ only will be there.
B cube will be I2, right? What will be B square? So this is
B-
0. Mhm.
BQ also will be not I3. I2
B cube
means.
is not I3.
May I2 means it will be not identity. B3 will be also I. What I'm just have to work it out little bit. Let me work it
Uh,
out.
other, have you tried it?
Just give me a minute, ma'am.
Okay.
Zero.
I think yes. Are you getting the same B square?
B square -1 it is coming. Like B square I'm getting 0, 1 row wise I'm telling ma'am 0, 1, 1, 1 I'm getting.
No, ma'am, it's
Okay,
correct.
it's correct.
I think it. Yes, ma'am.
Yes, B square will be 0, 1, -1, -1, and 0, 1, -1, -1. So this will be 0 and -1. This will be 0 and -1. This will be -1, 0, and this is 1, and -1, 1, which is -1, and -1, -1 plus 1, and that is 0. Okay, I need to check it again. Okay, and this is the same. And what is B cube? This is 1, 0, 0, 1. You can see this is, this will be 0, this will be 1, this is -1, this is +1, 0, this is 0, and this is 0, and this is 1, and this will be 0. Okay, so order of B is 3. Okay, similarly you can check order of A is 4. Now what about AB? So AB is 0, -1, 1, 0, and B is 0, 1, -1, -1. So what will be AB? That will be 0 and 1. So this is 1. This will be 0 and -1, -1, 1. This will be 0 and 0. And this will be 1 and 0. So this is 1. Okay, so this is AB. Now what about AB square? That will be 1, 1, 0, 1. 1, 1, 0, 1. So this is 1 in 0. This is 1. This is 1 in 1, 2. This is 0 and this is 1. Okay. What will be AB cube? So this will be fine. I'm taking AB square and AB. So AB square is 1201 and
It will be
1101.
1301.
Yes, so
1301.
this will
Row
be
row wise.
1301, right?
So
So
we have got the
actually,
pattern.
inductively, you can say AB to the power n for some natural number n. This will be 1n01. Okay. So can you have some natural number n which is
No,
0
no.
actually? No. This will be identity whenever this n will become 0. So obviously this is not possible. So no such finite n is possible. Okay, so order of AB is infinite. Okay. So if order of A and order of B both are finite, we cannot say that order of their multiplication is also finite. No, that is not true. By multiplication, I'm mentioning the binary operation of the group. Okay. If we reverse the case, order of A and order of B both are infinite, then can we have some case for which order of A, B is in finite actually?
So for the real matrix we have taken, so it may come, ma'am. I think so. It may
Hmm.
come.
Yes. And
Uh,
actually, you can take simple like set of numbers actually. That will also
okay.
work. Say we take this Z plus, this is a group, and we take A is say 2 and B is say minus 2. What is order of A? What is order of 2 actually? Order of A, say if order of A is n, then uh, we operate this A to itself n times and we get the identity element of the group, which is 0. Okay. I'm not writing A to the power n here. Okay. A to the power n is basically this, like A star, like this up to n times. So this is the meaning of A to the power n. So actually here we have n into A and that should be E. Okay. This will be the definition of order in an additive group. Okay. So what will be order of 2? To find order of 2,
Infinite.
we need to add 2 in itself. So 2 plus 2, that cannot be 0. 2 plus 2 plus 2 cannot be 0. So if we add 2 in itself, like um, in any finitely many number of times, we will never get 0. Okay. So order of 2 is infinite. Clear?
Okay.
There is no n belongs to Z plus such that n2 is 0. Similarly, like this will give order of 2 is infinite. Similarly, we can say order of minus 2 is also infinite. Now, what will be AB? AB means A operate B. Okay, that is here A plus B we need. So this is 2 plus minus 2, which is 0. 0 is the identity element. An identity element has one order, obviously. And obviously, if we like just put 0, this is the identity itself. Okay. So order of A plus B is 1, which is finite. Okay. So both are false. Neither this nor this is true. Okay. Now, what about the third one? So yes, uh, in any general group, AB and BA, they can be different, but their orders cannot. The orders will be the same. Okay. They can represent different elements, but they will have same order. So how to prove this? Okay, it's already 8:12. Uh, so I think I can give a hint for this and then we will continue in next class. Okay?
So next class will be say, same day, you know.
Yeah,
S-
same day.
Uh,
Tuesday from
yeah.
6 to 8.
Okay. So this is 12-week course, no, ma'am?
Yes. This is a 12-week course and we will have one more mm, tutorial session, either to summarize all the topics or to take any further queries or any advanced topics, whatever the case will arise. So,
Okay, okay.
so we will have 12 tutorial sessions weekly from 6 to 8 for 12 weeks, and then we will have an extra session either of 1 hour or 2 hours. Okay.
Okay, good night, ma'am.
So,
Thank you, ma'am.
okay. So, actually, for this one, for the third one, I claim that order of some x and order of G inverse xg, they are same. Okay. So how to do this? How to check this? So let order of x is m and order of G inverse xg, this is n. So this implies x to the power m is identity, and this implies that G inverse x g to the power n, this is identity. Okay. Now, x to the power m is identity, but what will be G inverse x g to the power m? What will be this? So G inverse x g, G inverse x g, when we do this, we will have G inverse x square g. So 2 times we will have power 2 of x. When we do this 3 times, G inverse x g, G inverse xg, and then G inverse xg again, then this will become identity, this will become identity. So we will have G inverse x cube g. Okay. So what will be this?
So by
This will
m
be
times it will be
G
e.
inverse x to the power m and then g. And x to the power m is basically e. So this will be G inverse e g. So this will give you identity. Therefore, order of G inverse xg, this will be less than or equals to m. Okay. That is n is less than or equals to m. We need to prove the converse also. So how to do that? Like, this is actually similar. What we do for order of A and order of A inverse, they are same, right? So x to the power, mm, now we need to consider power n of x. So x to the power n, what will be this? So power n is actually associated with G inverse xg. Okay. That is, we need G inverse from the left side and G from the right side actually. So this is G G inverse Xn G G inverse. Okay. Now, what is this? G inverse Xn G. This is G inverse. So what is this? This is basically G inverse Xg to the power n, what we discussed here. Okay. So this will give you identity as order of G inverse Xg is n. So this is identity. So from here you can conclude that uh, order of x is less than or equals to n, or m is less than or equals to m. So actually they are same. Therefore, order of x and order of G inverse xg, they are same. Okay. So now what I can do, what is order of AB? Order of AB will be order of B, A, B, B inverse, right? Why this because this is true, like order of x will be order of G inverse xg. Here G is any element from the group. So for this AB, we put it in center and then we apply B. Fine. So take B inverse and here simply B. You can do like which one? Both are same actually. Okay. So this is same as order of BA. So from this you can conclude that AB and BA, they have same orders. Okay. So time is already over. So symmetric groups, I will discuss that in another session. So any doubt till now? Uh,
No, ma'am. Thank you.
okay.
Thank you, ma'am.
Vaibhav?
No, ma'am, no, ma'am, no doubt.
Okay, so this was clear. Okay, so actually, I want a quick feedback. Uh, can I increase my speed? Actually, I want to cover
Yeah.
more examples.
Yes. Yeah. Yeah.
So,
Ma'am, wherever a doubt will be there, definitely we are going to ask in between. Wherever we are
sure.
understanding, so you can go little bit fast. No problem. I don't know
Uh,
what about Weber. I don't know.
uh,
Yes, ma'am,
yeah,
same goes
sure.
for me.
So, sure. Actually, like as I said, we can do one thing. Any specific or any advanced doubts, you can ask in comment section. I'll resolve those separately. And some doubts can come from upcoming topics, so that's also a problem. Okay. So in next session, we will focus on the current topics more. Okay. And my strategy will be in the starting of 15 to 20 minutes, I'll try to summarize the those week's lectures. Okay, like summary of theory, and then we will do questions. Okay, so what I'll suggest, before the tutorial session, please try to cover all the lectures by professor, and then we will discuss it. Okay. So this recording, I'll upload this on the YouTube channel, no problem. And this PDF will be shared with you also. So that's how you can find the, and actually for you too, I can show that. So yeah, this is the YouTube handle, Priyanka underscore NPTEL underscore TA. Till now, there is no video. I just made this channel separately for this course only. So you can note down this and mm, I'll upload the video there. Okay. Okay. So thank you. We will meet in next session again. Thank you.
Thank you, ma'am.
Okay.